As we begin section 2, we're going to be looking at the mechanics of an individual composite layer or a lamina. And to start with, we're going to use the stress and strain transformations that we learned how to do for general tensors in section 1. And we're going to apply those, again, to a single composite layer. So to begin, let's define what we call the global and local coordinate systems. When we look at a composite layer, a lot of times we'll characterize its properties in what we call the local coordinate system. So the plane of the layer we call the 1-2 plane. The fiber direction we'll say is the one direction. But then that layer is going to go into a structure for which we define a global coordinate system. And most composite laminates are usually loaded as plates and shells. So the global axes will have the XY plane as being the plane of the laminate, and so the Z-axis will be normal to the plate or the shell. Now similarly for the local coordinate systems, because the 1-2 defines the plane of the layer, the 3 direction is going to be normal to that plane. So in this case, the local 3-axis, the global Z-axis are going to be coincident. Let's take a little closer look at that. Here's a composite layer, and so these lines represent the fibers for that particular orientation, and so we define the fiber direction as, the one direction rather, as being the direction of the fibers. Within that plane, and 90 degrees from the one axis, is going to be the transverse direction too. And so you can see the fiber direction 1 is defined, its orientation is defined by the angle theta relative to the x-axis. Alright, so now let's go back to the transformations that we made in section 1. And we'll have to kind of get our nomenclature similar here. So on the left side we'll have our new composite lamina notation, and on the right side we'll have the tensor notation. So, as we just said, the fiber directions defined is the one direction, the 1-2 is the plane of the layer relative to the global x and y. Now, when we did this for the general tensor notation, we called the unprimed 1, 2, and 3 axes, that was the global, and the primed 1 prime, 2 prime, and 3 prime were the local, would correspond here to the local coordinate system. So, local stresses. In the composite lamina notation, we would call the normal stresses sigma 1, sigma 2, sigma 3, and the shear stresses tau 2, 3, tau 1, 3, and tau 1, 2. So you notice the order in which you show those. Normal to the 1, normal to the 2 direction, normal to the 3 direction. Now, corresponding to those again would be the primed values in the tensor notation, and we use that contracted notation from 1 to 6. Okay, so for global stresses, we're now going to have sigma x, sigma y, sigma z, the normal stresses, as well as the 3 shear stresses. And again, those would relate to the unprimed values in tensor notation. I know this is a little bit confusing, especially since we use the 1, 2, and 3 in both. But we're going to leave the tensor notation behind here really quickly and do everything else in our composite notation. Again, 1, 2, and 3 representing local, and x, y, and z representing global. Okay, but we take that stress transformations from section 1 and just substitute in our new values of local and global stresses, and there's our coordinate transformations. Now, we're going to, again, this will work for a 3-dimensional state of stress, but most of the time we're going to be only interested in a state of plane stress. So plane stress simply means that all the out-of-plane stresses are equal to 0. And of course, that's a good assumption for thin laminates. So the normal stress in the z direction, as well as the 2 shear stresses, tau yz and tau xz, are assumed to be equal to 0. So if we go back for just a moment, what that means is for this transformation is that we're not interested in sigma 3, tau 2, 3, tau 1, 3. We're not interested in sigma z, tau yz, or tau xz. Only the in-plane stresses we're interested in. Means we can knock out rows 3 to 5 and columns 3 to 5 and end up with a nice 3 by 3 matrix that will transform our stresses, in-plane stresses, from the global to the local coordinate system. And in shorthand, we're going to say that's the stresses local is equal to the T1 matrix times the stresses global. And again, this is the simplification for plane stress. Now, if I want to go from local to global instead, all we have to do is invert that T1 matrix. And so if you remember, in section 1, we showed how that we could symbolically take the inverse of a 3 by 3 matrix. And so if you go to the course pack notes right at the end of section 2, I go through that. And what it comes out to, and by the way, the determinant of that transformation matrix is exactly 1. And so you go through all those transformation equations, and really the only thing that you see is that happens is that the sign change here and the signs change here. But this is the T1 inverse matrix there. So shorthand, again, we would say the global stresses are equal to the inverse of the T1 matrix times the local stresses. Okay, so that takes care of the stress transformations. We also need to transform the strains as well. And so again, we can take exactly what we had. In fact, this is, without even changing the nomenclature here, this is what we had for the strain transformations, the tensor transformations. Again, primed representing the local and the unprimed representing the global. Now, instead of with the stresses, we just simply substituted our nomenclatures, but we have to do this a little bit different for strains, because if you recall this, we said that engineering shear strain refers to the total angle change within a plane, whereas the tensor shear strain is only half of that. So engineering shear strain is twice tensor shear strain. Okay, so if I want to write those equations in terms of engineering shear strain, then I have to use the gamma over 2 both here and there. So when I simplify this down to the 3 by 3, for example, epsilon 1 is going to be m squared times epsilon x plus n squared epsilon y, but then I come to 2mn times gamma xy divided by 2, so the 2's cancel out. Similarly for epsilon 2. And when I get down to gamma 1, 2, then of course I'm going to end up having to multiply by 2, and these 2's will cancel out. So anyway, what that boils down to then is as shown here. And so you notice that this this transformation matrix for strains is a little different than what it is for stresses. And so we're going to call that the T2 matrix. And in shorthand, we'll say, okay, local strains are equal to the T2 matrix times global strains. And if we do the inversion, once again, what happens is you only end up changing the signs of these terms here, but that is the inverted T2 matrix. So the global strains are equal to the T2 inverse matrix times the local strains. And by the way, these transformations are summarized on the first page of the summary sheets of the course pack. All right, so with that, what we're going to do next time is look at stresses and strains and relate those.